and do that. So if you're looking at what we have here now, it's a cubic function. I mean, as you said already, 1.10.1 was fine. So this is like what? H of x. A is like -1.
It actually wasn't, but we move. That I could have thinking it, looked at just the memo and be fine. But
Okay.
I was because okay, can we just go through 10.1?
Mm.
Normally, when you find the equation of a parabola, for example, you either use the turning point formula in the form of a open bracket x minus p and then close brackets plus q,
Mm.
or you use what else do you use the tn formula with two x-intercepts. So if a formula is like this and it's a cubic, what am I supposed to do? It just looked a bit funny.
Well, the fortunate thing is that our question is it's not too aggressive because look,
Yeah.
they're asking us to get h of x, right? But then h
Mm-hmm.
of x, as you can see the format here, the format of h of x, it looks like something that we can factorize without cracking our brains too much. Because look, both of these have x squared in them, like whether we like it or not. We can take out x squared as a foreign factor. And then you have a
You're right.
x plus b. Now looking at this some more, our sketch should always help us. Okay, let's just see the question. It says here the graph of h of x is drawn. They say the graph has turning points at the origin and b. And then it says a is the x-intercept. So what's important is this part here. This part. This part is super important. The reason why this part is super important is because um I think, yeah, depending on how far you are with like the functions and graphs course, what you
Mm-hmm.
already know is that anytime you have a cubic function, right? Anytime you factorize it, if
Mm-hmm.
a turning point is also an x-intercept, this graph factorized will always have two brackets that look identical, and then the third one will be for whatever this x-intercept is. So whatever this x-intercept is, right? I mean, like hypothetically speaking, here you could even put like x plus 0, x plus 0. And then here,
Mm-hmm.
let whatever this number is, you would put x. Let's say this was like a 4, no 5. If this was like a 5, here you'd put x minus 5 when this whole thing
Right.
was already.
I did. Well, I didn't. Like how you just took out the x squared. What I
Mm.
did is that I wrote it as what as the formula as the turning point formula, but then just said x minus x1 squared. So that part I did understand, but then yeah, the rest no.
Okay, well, I think for this question, the easiest way to put it is to say any cubic function when it is factorized, it's always in this format, right? A x minus x1, x minus
One
x2,
x minus x2.
x minus x3. So what we're
Mm-hmm.
saying is, as long as you see that a turning point is also an x-intercept, it means that
Mm-hmm.
two brackets will look exactly the same. You see, so here you would even just have two distinct x values, and then two of them. Wait, no, you'd have one distinct x value, and then two of them identical. Here you'd have x1 and then x1 again, and the second x-intercept. So according to our sketch, we only have this one, which is the one that kind of matters, because this one is the one that's telling us that this. Let me just do this in two separate lines so that we can refer to both of them. So because of the way our sketch is like set up, our sketch is already telling us that okay, this is a 0, and then it's a 0 again. You see,
Mm-hmm.
that's the first thing. And then whatever this is, I mean, like, if we don't want to make our life too complicated, let's just move this down here. We don't want to make our life too complicated. Here we just have h of x is equal to a. This is just x. This is also just x. And then this is just minus x2, you see, which would have a x squared and then x minus x2. So like this, you can see it's not very nice to look at. It's not neat. It's not conducive. You know, it doesn't look like this is really helping us
Mm-hmm.
to like what you call like answer the question. You get,
Right.
yeah. So what you would much rather than use is this specific question, because this is more like generic. This is more generic. But then if we're now looking at what is actually given on our question, this is what is given. We're given h of x is we're given h of x is a x cubed plus bx squared. You see? And then what we said is, okay, fine, whatever we're going to do, right? Let us just factorize first. So we factorize by saying that, okay, fine, f h of x is equal to x squared, and then this bracket. So what we know is, as long as this is factorized, we can say that the first bracket equal to 0, or the second bracket equal to 0, right? Because you're factorized. Remember, after factorizing, you can say one bracket is equal to 0, or the other one is equal to 0.
Oh, okay. Yeah, we just just lost it. Okay.
But are you found now?
Yes,
Have you
I'm bound. Yeah, boo.
nice? Yeah. So here you can just square it both sides, and then x is equal to 0, which is this x-intercept. Fine, perfect. But then the other one, if you're going to solve for x here, you're gonna get something like ax is equal to minus b. Solving for x here, you're gonna have x is equal to minus b over a. You see?
Mm-hmm.
Yes or no?
Yes, I do see. Sorry, I'm trying to. Yeah, yeah. I see.
Yeah. So without us getting too overwhelmed, right? This is just giving us one x value. This is giving us the other x value of our what you call of this picture. So whether we like it or not, um, whether we like it or not, the x value here is just negative b over a. You see? So us knowing that, if you think of it nicely, right? If you think of it nicely, let me try and make. Let's try and keep things simple for ourselves here. If you think of it nicely, right? Having to have used that way of thinking. Do you see that here we have an equation? It has what do we have here? Okay, let's pause here. Let's pause here. So having to have paused there, going back to the information that we have about our sketch, we can see that, okay, this root, the generic root, yeah, it seems like it's bombing out one way or the other. It seems like it's
Mm-hmm.
bombing out. This way, it has gotten us this far. We have an equation here that has, you know, minus b over a, which is fine. But then let's not forget the simple things. When I say let's not forget the simple things, I'm thinking of how there's a whole b given here, and it's a turning point. You see,
Mm-hmm.
so all that information is like super valuable, because when we're given a turning point and an actual coordinate, I mean, like, without even us having to have maybe thought about these generic methods and all that, right? I mean, like, keeping your life simple. Let me do this. Keeping your life simple, right? Based on like different examples that you would have done and all that. If you're looking at a question like the one we're given, right? It's not too bad like the others. Because normally if you had like three whole variables to work out, then all the things that we're thinking of now, they may be valid, factorizing, blah blah blah. But then here we're given something that is more valuable, a turning point and its actual coordinate. So this is how this is useful. Firstly, in the equation of h, do you see that we have two variables? And the one thing you'll always hear me say is that anytime you need to work out two variables, one thing that is very
I'm
useful,
multi-units.
yes, look at you, is to try and solve them simultaneously. So far we have b, it's a full coordinate given, 4 and 32. So meaning you have an x value
So
here.
are we shying away from are we shying away from the x equals 0 and x equals negative b over a, or we're gonna sub in that?
Oh no, for now we're shying away from it. because this is
Okay.
more generic and it's more heavy. We want to keep it
Oh.
light here because it's just 5 marks. They've given us a turning point, and we're just looking at 2 variables. It's not so bad. So what's going to happen here is you have an equation in terms of A and B. So this is just like, what is 4 cubed? No. What is 4 cubed? 4 times 4 is 16. 16 times 4, like 64.
It's 64.
16b. Very good. So here we're going to have an equation in terms of A and B. Let's maybe isolate B.
Right.
2 minus 64a, 16b. So let's divide both sides by 16, right? Right?
Right.
Divide by 16, divide by 16. So here you're going to have B, and then here you're going to have 32 over 16. Also here 16. Oh, no. That's wrong. There we go.
Right.
You see? Yeah.
Mm-hmm.
So this is like a 2. This is like a 4a. You see?
Right. I see.
So this we can label it equation 1. And then the other one. So now we could be thinking to ourselves, okay, fine, we have an equation that is A and B. We need another one. That's where this comes in. It's a turning point. A turning point is special. The reason why a turning point is special is because we know the gradient here. The gradient is equal to 0. You see? And the gradient is useful to us if we use the gradient equation. The gradient is a 0. Meaning we can just think of the gradient equation of our graph and throw in gradient as 0 and throw in an x value of 4 in that equation. It will give us a lot of other stuff that we may need. Let me repeat. We have the gradient here. It's a 0. And we have the x value here. It's a 4. That is useful to us in the gradient equation. See, the gradient equation of our, why am I using f of x? Let me use, it's h, right? We're dealing with h. So let me do here h of x. We know that the gradient here is a 0, where the x value is a positive. So we just need the gradient equation to give us a second equation to work with. And this is what I mean. H of x looks like this. It's a coordinate equation. That's how we put in a coordinate. And we put in 4 and 16. Done. I mean 4 and 32. So that was useful. Now we need to put a gradient and then x value. So let us do that. So we need a gradient equation here. A gradient equation will look like this. 3 times a is like 3 ax squared. Because 3 times a is 3a, right? And then 3 minus 1 is a 2. So here also differentiating it is going to be 2 times b, which is like 2b. And then 2 minus 1 is just a 1. So there's x to the power 1. So now you have a gradient equation. And remember, in this gradient equation, we can throw in a gradient, which is a 0. And we can throw in an x value where that gradient is a 0. We know that the gradient is a 0 where the x value is a 4. You see, this is going to give us another equation that has a and b in it.
Yeah.
Yeah, it is. So this is
16, yes.
16 times 3. What is 16? Oh, no. My brain is not working.
16 times 16 times what?
3. I think it's 48.
Let me check. Yeah.
Yeah, that's a good idea.
It is.
Yeah. And then here we can just divide. We can just take the 48 over to the other side. It's gonna be negative 48. And then we can just divide by 8 here on both sides. So divide by 8 here. Divide by 8. What is 48 divided by 8? Is it like a 5?
Negative 6. It's a 6.
Yeah. That was a flop. But this is a bit Is it reassuring? Not really. Because this is supposed to be positive. So there's something wrong here. Do you see? There's something wrong here.
Why would it be?
Because B is oh no. It's negative 6a. So
Oh,
the final answer.
I wrote that down and I'm looking at what you wrote down. I'm like, oh, what's going on?
Yeah, I forgot the a is still there. So here we have a second equation, you see. Equation 2, equation 1. So we can just throw 2 in there. Equation 2, we can throw it in there, do you see?
Mm.
Yeah. So let's put an arrow even. We're gonna throw it in there. So let's see here. Equation 2 going into equation 1. We're gonna have B is what? B is negative 6a, you see.
F6A.
So yeah, so this is like 2 minus 4a equal to negative 6a. You see. Solving for a here, we can see this goes to the other side. Negative 6a plus 4a, which is like negative 2a. And then divide by negative 2 on both sides. A is negative 1. You see it?
Yes, I do.
Perfect. Nothing crazy, nothing major. So as long as we have a now, we can also just then get b now. Because remember, b we said it is equal to negative 2. No, it's negative 6a.
Right.
So it means that b is equal to negative 6 times negative 1. B is a 6. There you go.
Okay.
That's the way we like it. So,
Going back to 10 point. Pardon?
going back to what?
10.3.2, the concave down.
Wait, hold on. Before that, even the point is, you see what we did with this question. Us, if the point where you're going to like be able to just jump directly to knowing that okay, fine, turning point, coordinate, blah 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 blah, and it's also like a simple equation. Like the only way you're going to like jump directly to that way of thinking is if you have like gone through like multiple examples. You see? Because the more examples you're gonna go through, the easier all this is gonna get. Do you get it?
Yes, I do.
Fantastic. Anyways, let's make this